So now does it look fine to you? But just try to write a bit larger so that the text becomes visible.
Okay, but it's not zoomed.
No, it's completely zoomed out.
No, but I mean like, is it natural? Did you zoom out?
No, sir. It's like it's normal mode. Like it's not zoomed out.
The record button is on? Okay, so sorry for Okay guys, you can leave. Those guys who want to leave, it's okay. Like, we can mark you. And we can redo whatever I've done today. So no problem, but I don't want to miss my class. Yes, so today there was some confusion. I apologize for that. I thought that it's 2:30. Yesterday I had a PG class and that also started at 2:30, so I had the same thing. Okay, so we were doing double integration method. I'm not going to solve this problem for you guys, but I'll get the moment equation and then you can do it yourself. I'll give you some assignments. One of you will take a picture of that and then post it on your WhatsApp so that like all of you start working on it. I need that assignment before next Friday. Okay, so that will be problems involving double integration method. I was asked in the previous question how could we do the uniformly distributed load using double integration method. That's why I will work out the moment equation for you. So this is a beam, okay, which has got a UDL. It's a patched UDL or partially applied UDL. It's cantilevering out and subjected to a 600 Newton load at the edge of your edge. So now, how can we work out the moment equation? What do you think? How can we work out? Like, look, there is a problem over here. If we take our x over here, let me get my. If we get our x, if this is our x, yes, then what will be the issue?
Sir, it's already.
If our x is over here, yes, then how can we work out the moment for this load, 400? I mean, like, how can we incorporate this 400 Newton per meter in our moment equation?
Sir, its moment arm is.
It can be.
1.5.
Look, this is x minus 1, minus 2, and what else?
Sir, 600 Newton force will be okay.
You can't say, okay, so if you.
X minus 2.5.
X minus 2.5.
X minus 2.5.
What do you mean x minus 2.5?
1.5 is the centroid, sir, and then one behind 2.5.
No, but how would you work out this length?
Sir, the load will act at the center of the beam. It will become 1.5 meter and the 1 meter from the previous one.
No, but we are not converting it into a concentrated load. We want this load to be in terms of x. Then in the moment equation we will get x power something. So how can we incorporate this 400 Newton per meter in our moment equation?
X minus 5.
No, we want to have one equation. Two equation doesn't serve the purpose. Main idea is to get one equation. So how can we do that?
Sir, we'll cut the second from this side.
No.
So x y के terms में x minus 2.
Whether it's this side or that side, it doesn't matter. Okay, it's the same issue. But what is the issue? First of all, try to understand. If my x is not defined, then what will happen? If my x is not defined, isn't it? It can vary.
Yes.
Okay, and it can vary between these two points.
Yes.
So which is like from the left support 3, 4 and 5. 5 meter till 7 meter from the left support.
6 to 8.
Okay, so sorry, 6 to 8, 6 meter till 8 meters. So that's the range of this. Now, how can I include this 400 Newton per meter in my moment equation?
तो मोमेंट के इक्वेशन बनाना जरूरी क्यों है?
Because if you have more than one equation, then you have to make sure that those two equations are compatible with each other. So in other words, you will get another constant. So for example, if I have got something like this, okay? If there is one equation in terms of x and there is another equation in terms of x, so your moment will be m1 plus m2. Would it be like that? No, it's not going to be like that. You will have everyone separately.
Yes, sir.
So d2y by dx square is equal to m1. Okay, you will work out your equation, which is like this. So you will have r1 x minus w x square by 2, okay, and you will have another one e1 d2y by dx square, and that will be m2, which will be r1x minus w x minus
whatever the length will be given to us.
okay, so let this be L1.
X minus L1.
So x minus L1 w into
So this will also be
x minus L1 square divided by 2. Okay, now we will have two equations. Now you have to correlate these two equations somehow. So once you, because in this equation you can apply the boundary condition for this support, okay, but you can't apply the boundary condition for that one.
Yes.
And in this one you can apply the boundary condition for this one but not for the previous one. So there has to be, so what are you, so how can you overcome that?
By making one equation.
You can overcome that by saying that your elastic curve at this point, which is the range, yeah, the deflection is the same and the rotation is the same. Do you understand my point?
Yes, sir.
So that is an additional condition you have to impose on this. Then these two, you have to join them somehow, because this is one equation. You have to derive one equation. But how would you do that? You have to ensure some compatibility between both sides.
तो इसमें C1 और C2 की वैल्यूज आएंगी दोनों की.
C1, C2, this one will have its own C1, C2. This one will have its own C1, C2. Yeah. So imagine this one will have C1, C2 prime, and this one would have C1, C2 double prime. Okay, so you have got four constants now. You have got, yes. You have C1, yes, you have got four constants now. So now two constants are based on the boundary conditions. Agreed?
Yes.
And two constants you will derive based on compatibility of the curve. The curve is the same, isn't it? So the displacement which you get at this point, which is the range of the first equation will be within some range, isn't it? This will be x between 0 and L1, and the other one will be x between L1 and say capital L. Okay, that is the range, for example. So in this one you will get d2y by dx square. So you will get the slope and deflection, and in this one also you will get slope and deflection. Both of them at the boundary, the slope, I mean like the deflection and the slope at the boundary would be the same. So there will be another, so that is another exercise which you have to do, because at the end of the day you need one elastic curve. You don't need two elastic curves you have to have one elastic curve for the whole structure. That's why so in order to avoid that, we use one moment equation,
Yes.
and automatically we get one elastic curve. Do you understand my point? So that's why we avoid this thing. Now the problem is how to do that. Please remember that in order to use this equation will work if where is your UDL placed? Your UDL is placed close to the support. Okay, so it is right next to the support. That's why you are able to use this, isn't it?
Yes, sir.
Agreed? Yes. So in our case, what should we do? Our UDL is offset from the support. So what we can do is we can have the same UDL applied like this and another one applied like this. Can we do that?
Yes.
The effect will cancel out obviously because they are opposite.
Yes, sir.
But this is just to derive our one moment equation.
Yes.
And now it's the same as this problem, isn't it?
Yes.
Do you agree with me?
Yes, sir.
So, should I wrap it off? Should I remove it? So, what happens is that we have the moment equation, okay, having a UDL starting from the support, from the left support. Now we can use this x, okay? Why? Because we won't have that issue of working out UDL in terms of x and also its lever arm in terms of x. So the equation is EI d2y by dx square is equal to, help me out, 500 x
Plus 400
minus 400
times x
minus 2.
2.5.
No, sir. 400 into 4. Sir, first we will multiply 400 with 4 so that we can get the total.
It is acting on the 4 meter section.
No.
Total
What
area,
I mean, what we want is this whole thing in terms of.
So but first we multiplied
First
400 with 4 meters. So in order to calculate the whole applied load, because it's UDL, it's not point load, it's acting on 4 meters.
Sir, no, this is our UDL now. This is the UDL.
Yes, sir.
Okay, so how can we find out this length in terms of x? This is x minus what?
X minus.
Then x minus 4 or x minus 4 divided by 2. पूरी को ये बन गई.
So why are you saying it's x minus 4?
X plus 4.
X minus 4 is X minus 2 होगा. X minus 2 होगा सर.
X minus 2.
क्योंकि वो बिल्कुल सेंटर में करेगा तो वो हमें ये वाला डिस्टेंस चाहिए.
We need this thing. We need this distance. So how much is this distance? x minus, how much is this distance? X minus
X minus 4, sir.
4, sir.
1 is UDL, sir.
Sir, this is x minus 2 and something. Sir, this is
Sir, what if we start from right side?
Sorry?
The right side start from
So what should, okay, so is this thing working?
No, sir. No.
We have got the same problem. So let us try, so what if we try it from the other side? Will it work?
Yes.
Instead of this one, if we do, let us check. If we do this thing, will it work now?
Yes, sir. Sir, where would we cut the section? At this corner? No, before 500.
Sorry?
Sir, where would we cut the section now?
Yes, sir, it will be now x minus 1.
It will work. Yes,
Will it work?
Yes, sir.
Yes, sir.
Now it will work.
Now it will work.
Okay, so what will we do? We have 500 times x minus 400.
X minus 1. X minus 1 by 2.
Yeah, that is for this UDL. The UDL which is facing up, that one is plus.
Plus 400 into x minus 4.
Sir, are we taking movement from right side or left side? Right side.
We are taking movement about this point. And 1300 into x minus 6. Okay. Does it make sense to you? What have we done? We had a patched load. Okay. This load, now this load caused difficulty in writing moment equation. What is the difficulty? If we take x at the extreme, the maximum x possible. If we take the maximum x possible, okay, just slightly less than the extreme end. In other words, whatever the length is, just slightly less than that, so that it covers the last section. Okay, the last. So if we take that x, we can't work out our moment equation for this one. This is not simply just 400, you multiply it with 3 and you take it. No, because UDLs or UBLs we take in terms of x. This is, and that's what this differential equation should give us. Okay, this is a differential equation in terms of x. Okay, so we must have all the UDLs and UBLs in terms of x. Okay, it is important for this differential equation. Now we place so we have two options. Yeah, either we place equal and opposite UDL on the left hand side, or either we place it on the right hand side. So we said that let's place it on the left hand side. Now if we place it on the left hand side, we face the same difficulty. Why? Because if it is over here, what is the lever arm? How can we work this thing out fully in terms of x? Okay, because why? Because we don't know the limit of this one. We don't know whereabouts is this. The only thing we know is that we know the range. That's all we know. So we are faced with the same problem. So in order to overcome that, we decided that let us put equal and opposite UDL over here. If we put it like this, then what happens is that from this x we can easily subtract this distance, yeah, and similarly, I mean, we can work out our moment equation straight away.
Okay.
So we are taking moment on this side, right?
We are taking always moment at the end of x. That's what happens, isn't it? When you are asked to find out shear force bending moment, you want to do it from first principle. What do? You take it at a distance x.
Sir, plus 400x minus 4 divided by 2 for upward uniformly distributed line. So what about downwards uniformly distributed?
Which one? This one.
That major.
This one.
Yes, sir.
But this one is already accounted for. It's here. 400. This is x minus 1. So according to this equation, the whole thing is under union. Okay?
Yes.
And that one we add. Why? Because in order to remove the effect of this one. The fictitious union which we apply. So that is, so using this. And what are the boundary conditions?
Sir, 0.
Deflection, zero.
Sir,
एक boundary में
The boundary condition
दोनों
is,
reaction जहाँ पे आ रहे हैं वहाँ
sir, at both reactions it is 0.
so imagine this is A,
When x is equals to 0,
C, D. So boundary conditions are at
x is equals to 0, y is equals to 0.
y is equal to 0 and x is equal to 0.
Yes.
That is the first boundary condition.
And
And
when x is equals to 6, y is still 0.
when x
6.
support का
because the elastic curve is going to be something like this. So at this point also, your deflection is. So this is your first assignment you have to do. You should get for E is equal to
Deflection.
EIY.
Why deflection?
This is what you should get.
So what is this? E1y? Sir, at what point, sir? Minus 80. Point. At x is equal to 8, okay?
At x is equal to 8, you should get EIY is equal to this.
Sir, this is basically deflection.
This is the deflection.
Yes, sir.
So this is your first assignment.
maximum आ जाएगा
Sorry?
ये maximum आ रही है distance जब हमारा
No. This is the deflection at this point.
It may be maximum somewhere else.
Yeah, it can be maximum somewhere, either over here or over there.
Yes.
dy by dx 0.
Yeah, just make dy by dx is equal to 0 for this one. Yeah, and find out. Okay, so Previously we did this. Then we just make dy by dx equal to 0, find out x, and then you plug it back in the deflection equation and you will get the maximum deflection. And you can compare it with this one. Okay? Because this is one deflection and there would be another deflection in the middle in this path.
Yes.
And it depends like which load will cause more deflection. Because if this load is higher, what happens? This is trying to push up. This is trying to reduce this deflection, isn't it?
Yes, sir.
Yes.
But if this load, which is over here, is higher, this is trying to push it down and increase this displacement. So we don't know really whether this one or this one is gonna govern. Okay? So you can find out EIY at this one and compare it with the maximum deflection, with the deflection in the middle. Okay?
So where rotation is 0, deflection is maximum.
Yeah.
Okay.
Wherever your deflection rotation is 0, because if you make a slope of that, this is just like a maximum minimum.
Maximum.
Okay, so if your rotation, wherever your rotation is 0, dy by dx,
Yes.
at that point your deflection is maximum. This is the first question. The second one.
क्या
आप लगता है कि आप
नहीं नहीं ये सब बता रही है पिक्चर कैच यार
चार इंचेस भी दे
Sir, the dy by dx, sir, the equation for rotation will go into cubic, sir. Sir, the equation for dy by dx, it will go into cubes.
Yeah, but you can use programmable. Okay, so this is another.
Sir, then for sir, linearly distributed loads, it will go into fourth power.
Sorry?
Sir, when we will do that varyingly distributed loads, it will go into fourth power.
Yeah, basically I would do. Okay, so we will stick to only UV.
ये थर्ड में देखो दो दो
आफ्टर डबल इंटीग्रेशन इसका भी पावर 4 हो जाएगा
Sorry?
कांस्टेंट फाइंड करने के लिए x का पावर 4 हो जाएगा
Yeah, but what's wrong with that? No, you can work it out. You can easily work this thing, this one out. This shouldn't be a problem.
उसमें 4 से 3 से ऊपर है
रेडियल में पावर 4 का दिया था लेकिन सिलेबस में नहीं है
पावर तक है
3 तक
ये 4 तक
यार dy by dx को 0 करना है ना
Okay, so you get the elastic curve for this problem.
क्लास का
वो असाइनमेंट फिर नेक्स्ट वीक सबमिट करें सर वो जो आज क्लास नहीं ली उन्होंने वो असाइनमेंट का क्या
नेक्स्ट फ्राइडे है ना
नेक्स्ट फ्राइडे
स्माइल की नहीं है सामने आना मेडिसिन
मतलब हमारे साथ
ओए यार ये तो वेरिएबल्स की टर्म में है। नहीं इतना मुश्किल नहीं है। वो यार जीरो लगे हुए हैं। नहीं क्या एक
Sorry?
Question number 2, sir.
Yes.
हम boundary condition को एक ही given है.
No, there are two. What are the boundary conditions in question number 2?
सर रोटेशन
Rotation will
रोटेशन will be zero
and
deflection
deflection is zero. Okay. So in the next class, this question can be. But next class, I would need a bit more time. So what should we do? What time should we start?
सर मंडे
No, Monday is
you
9.
will have to
No. I can't. I need an extra half an hour at least.
Tuesday after
सर on Tuesday sir from 12:30 to 2
No,
sir from 1:20